Today we're going to look at Fourier transforms, which are a kind of integral transform. And what that is, it's just an operation you can do on a function to turn it into a function in terms of something else. So it'll be the same description of the same physical scenario, but one will be a function of another. So if one is a function of time, there's units of time, so seconds. If you do a Fourier transform, you'll get a function in terms of rate per second, in terms of frequency. If you have a function in terms of length, distance, units m, you'll get a function out which has the same physical scenario in terms of spatial frequency. So we see these things in real life. Our ears, for example, perform Fourier transforms, believe it or not. So if we were able to see sound waves, we were able to see this movement of particles in the air. So we'd have this thing in terms of space, of length. But we don't experience that as a whole bunch of movements. We experience that as pitch, as frequency. So our ears take this information, which is in terms of movement, and translates it into something that we interpret as frequency. So the Fourier transform would look something like this. So here's a sound wave, and those sound waves are longitudinal, not transverse like this here, but just for simplification. And we experience this. So this is in terms of space, and this is in terms of frequency. So we get one frequency, which is there. That's what a Fourier transform would look like for sound, for a sound wave as interpreted by our ear. And it would go the other way around for speakers. Speakers perform the reverse of this. They get information as a pitch and then translate that into movements of a speaker. And then, so it's the inverse of that. So if you do a Fourier transform twice, you get back what you started, more or less. So let's look at the maths of it. Fourier transform, we have a function in terms of something, let's say t. In terms of time, okay, which equals blah blah blah. Fourier transform, which is a different function marked by this little hat, in terms of frequency, which is equal to, how do we do this, 1 over 2 pi multiplied by the infinite integral, or infinite space of the original function, multiplied by e minus the product of the two variables that we're looking at. So in this case, frequency and time. All that's differentiated with respect to time. So by the time you finish this transform, you see we're integrating with respect to t. So any t variable term will disappear. It will be replaced with constants, because we have limits of integration here, even though they're infinite limits. So that's how you would do a Fourier transform. So let's just look at a quick example. And we'll look at the example of just a square pulse. Okay, so it's going along, this is 0, it doesn't look like 0. Then it goes up, and it's a square, again doesn't look like a square, stays there. You might have heard of this as a top hat function. So this is just a unit step, say that's 1, and we'll make this 1 as well because it's a square. Minus a half, and a half. So our Fourier transform, let's say this is, it's just for consistency, let's say actually let's just call this y and x. Without thinking of too many physical things, let's just do it purely mathematically. Y and x, so our function of y, or a function of x rather, is, we're going to have to split this because it's not a smooth function. We've got to split it into different things. So so if fx is 1 for the interval of between -1/2 and 1/2, and it's 0 everywhere else. Let's just write elsewhere. So this is our function. We want to transform it in the terms of the conjugate component of what x is. So our function in terms of some new variable, let's just call it s, is equal to 1 over the square root of 2 pi. Don't worry about where this comes from. This is just a factor that helps whenever we do the Fourier transform again for it to be close to what it originally was. And we have an infinite integral. And multiply it by the function of x e minus s x times, I'll differentiate with respect to x. Now I have put my I've drawn this graph quite strategically. You notice this function is the same on both sides. We call that being an even function. So this function is even, so that means that f of x is equal to f of minus x. So if I go and look at f of 1/3, which is here somewhere, it's the same, it's 1. F of minus 1/3 is 1. So we have an even function here. Now if we think back to, hopefully you're familiar with Fourier series, or the Fourier theorem, which is about Fourier series, which says you can build any periodic function that's reasonably continuous out of various sine and cosine waves just stacked together, and you can do that for square waves. It's in reality it's quite inefficient, but this is an infinite sum within a small bound. Anyway, it doesn't work infinitely, but within a small bound, that's a Fourier series of a whole bunch of sine and cos waves. Except, well, you can do that with any function. In this case, because it's an even function, it's just a sum of cos waves. Think of what a cos wave looks like. It is symmetrical about the axis. So if we were adding sine waves to that, because they're not symmetrical about the axis, it wouldn't work. It wouldn't make the shape quite right. So we just got to add a whole bunch of these together. Then eventually it would look something like that, and that would smooth out eventually. So that's how we would make them, and that's really what, in a sense, what a Fourier transform is. So if we remember Euler's formula, E I theta equals cos theta plus I sine theta. So this is really cos, cos plus sine on the imaginary axis. So we're by doing this, and we have an infinite sum here. So we're adding infinite numbers of cos and sine waves with different coefficients every time, which is what we do in a Fourier series according to Fourier's theorem. So since this is an even function, we can ignore this imaginary component here. So in this case, we don't need to use an exponential function and have all these imaginary numbers and stuff going on, we can just write it in terms of cos. So if I take my old Fourier series, I'll just write it up here, f of s equals 1 over root 2 pi infinite domain f of x e to the minus I x s with sx next. Last time doesn't matter. So in this case, not all the time, just in this case because it's an even function, what we can do is we only put over half the domain now because it's even. It's the same on both sides. Or sorry, I'll save that for a bit. So it's all the same. F of x times cos x s. Yes, it's cos xs dx. And what I jumped ahead of myself and did there was, because this is an even function, we could half the domain, or this area of integration, so we don't have to go all the way to minus infinity. We can go to 0 because it's halfway in the middle, and then just multiply it by 2. So 2 up here. Or I could divide top and bottom by root 2. I come up with this, which is the conventional way of writing the cosine Fourier transform, as it's called here. So then, remember our function, it was a square pulse wave, which is 0 everywhere. Really, it's 0 everywhere apart from this one place where it's 1. So we can forget about all of this 0 nonsense here, and we can just make this guy into a 1. So that's just cos there, and make the domain. Remember, we're forgetting about this half, negative half, because we're multiplying by 2 and using the same. Yeah, for half the domain, just multiplying it by 2, and then this happens at a half, remember, because it's a square wave. So a half becomes the domain, so integrating between 0 and a half of cos xs with respect to x, all multiplied by 2 pi, dead easy. So we go on, and that gives us 1 over s sine x s half and 0. Okay, and we know, let's look at a sine graph. That's what it looks like. What's a sine? Sorry for the squeaking. What's a sine graph at 0? It's just 0. So this becomes 2 over pi 1 over s sine s over 2. And what can we do? We can call that 2 over pi s squared sine s 2, which is now our function in terms of s. Now we see that the x term has completely disappeared here. We're not looking at that anymore. We're looking at now the conjugate of that, which is s. So if we were to think about that slightly more physically, if the units for x, so the units of s equal inverse of the units of x, and vice versa. So if this was some sort of movement in space, we would now have a term in terms of spatial frequency. If this was some sort of time step, we would have something in terms of hertz of generic frequency or rate. So that's it. If we had done it without the simplification with the cost, we would have come up with the same answer. It just saves a bit of time, saves you working with imaginary numbers and the likes of that there. So that's a basic example of a Fourier transform.